Creating a ship anchor is a complex process that requires precision, strength, and expertise. This process begins with a large piece of steel, heated until it glows red hot, indicating that it is malleable enough to be shaped. Under the guidance of skilled blacksmiths, the steel is hammered with a force equivalent to 1 ton. Slowly but surely, the raw material is forged into the shaft of what will become a massive ship anchor, capable of withstanding the relentless forces of the world's oceans. The choice of material is crucial in anchor manufacturing. To endure the extreme conditions of the sea, the anchor must be made from forged steel. This material is both elastic and durable, providing the necessary strength and flexibility to resist breaking under stress. In contrast, if an anchor were made from cast iron, it would be too brittle, risking fractures under the heavy loads imposed by ocean currents and tides. At Hammerbeck GmbH, a renowned chain factory in Duisburg, Germany, workers retrieve a fresh steel plate, which will be further processed into anchor components. The first step involves cutting the steel using a specialized torch that operates at temperatures exceeding 2000 degrees Celsius. This intense heat allows the flame to slice through steel plates up to 40 centimeters thick with ease. The ability to handle such substantial thicknesses is essential for creating anchors that can weigh up to 10 tons. The anchors produced at this Duisburg facility, known as Drana Spezial, are designed with unique features that set them apart from standard anchors. For instance, when a ship raises one of these anchors, it automatically aligns itself to avoid damaging the ship's hull, then disappears into the anchor pocket, a recess designed to house the anchor securely when not in use. The assembly process is a collaborative effort, requiring precision and teamwork. Workers in the hull begin by positioning the massive components of the anchor. To ensure stability during the assembly, they employ tacking welds, which temporarily hold the parts together. Given that the side elements of the anchor weigh several hundred kilos each, cranes are used to lift and maneuver them into place. Once the components are in position, final adjustments are made with a cutting torch to ensure a perfect fit. To prevent the anchor from tipping over during the assembly process, additional welds are applied for stability. A critical step in anchor manufacturing is attaching the shaft to the anchor's head. This involves inserting a 50-kilogram bolt into the shaft hole, a task requiring considerable strength and precision. The head of the anchor alone weighs about 3.5 tons, and when combined with the shaft, bolt, and 2 smaller steel plates, it forms a joint that allows the anchor to function effectively. The Drana Spezial anchor, developed by Hammerbeck GmbH over 40 years ago, is a type of clip anchor known for its robust and reliable design. After the components are assembled, the workers weld the joint securely to ensure that the anchor can perform as required. The shaft must be able to tilt forward up to 40 degrees, a design feature that allows the anchor to embed itself in the seabed when deployed. To prevent excessive tilting, steel plates are positioned in front of and behind the joint. With the anchor's main structure assembled, the next step is to complete the final welding. Shielded gas welding is used to create welds as strong as the steel itself, ensuring the anchor can withstand the harsh conditions of the ocean. However, the anchor is not complete without the swivel joint, a critical component that connects the anchor to the ship's chain. The swivel joint allows the anchor to rotate freely, preventing the chain from twisting as the ship moves. The assembly of this component involves attaching a special ball joint to the anchor, followed by securing it with a massive threaded nut, which is then welded to prevent loosening. Before the anchor is ready for use, it must pass a rigorous stress test. The anchor is subjected to a force of 120 tons using a specialized machine to ensure it can withstand the pressures it will face in the ocean. Only after successfully passing this test is the anchor deemed ready for deployment. The final step in the manufacturing process is applying a protective bitumen coating. This petroleum-based material is highly water-resistant, providing a crucial layer of protection against the corrosive effects of seawater. The coating ensures the longevity of the anchor, allowing it to function effectively over many years. The cost of manufacturing such a massive and highly specialized anchor is significant, with each unit priced at around 30,000 euros. However, given their critical role in maritime safety, these anchors are a worthwhile investment for ocean-going vessels worldwide. Anchors like the Drana Spezial from Duisburg exemplify the craftsmanship and engineering excellence required to produce reliable maritime equipment. A semi-automatic anchor chain making machine is a specialized piece of industrial equipment designed to fabricate anchor chains with increased efficiency and precision while retaining some manual control. These machines are commonly used in shipyards, marine industries, and manufacturing plants where heavy-duty anchor chains are required. The semi-automatic nature of the machine means that while certain processes are automated, such as the shaping, cutting, and welding of chain links, human intervention is needed for tasks like feeding raw material or overseeing quality control. The machine typically includes mechanisms for bending metal rods into precise link shapes, welding the ends of the links to form a continuous chain, and cutting the chain to specified lengths. The operator is responsible for adjusting settings, monitoring performance, and performing maintenance when necessary. This type of machine strikes a balance between full automation and manual labor, making it ideal for operations that require flexibility and customization. It allows for quicker production compared to fully manual processes, but with more control over specific aspects of production than fully automated systems. Moreover, semi-automatic machines are often more cost-effective and require less sophisticated maintenance compared to their fully automatic counterparts. Chain production at Pewig is a process where precision and quality are paramount. The journey begins with the wire, which is carefully cleaned and positioned. Every aspect of its length and curvature is precisely measured to ensure consistency. As in chain manufacturing, nothing is left to chance. Each link is interlocked with precision, forming a strong and reliable chain. Welding is a crucial stage, and at Pewig, every link is treated identically, eliminating any notion of a weak link. This consistency is further reinforced by marking each chain with a brand logo, quality grade, and a unique code, offering customers assurance of the product's authenticity and excellence. The durability and toughness of Pewig chains are then solidified through a specialized heat treatment process, a stage that excites true enthusiasts who understand the importance of these qualities in a chain. Surface finishing follows, with options like sandblasting, electroplating, or environmentally friendly painting, ensuring that each chain not only performs well, but also looks refined. Quality control at Pewig is rigorous, with each chain subjected to stress tests using diamond needles, ensuring they meet the highest standards. Oxyfuel gas cutting, OFC, is a widely used thermal cutting process for metals, especially for mild steel with considerable thickness, such as 850 millimeters. This method employs a combination of fuel gas and oxygen to achieve high-temperature flames capable of melting and severing the steel. Typically, acetylene is the preferred fuel gas due to its high flame temperature, though propane or natural gas may also be used. In the process, a preheating flame is first applied to the steel surface, raising it to its ignition temperature, typically around 700 degrees Celsius for mild steel. Once the desired temperature is reached, a high-purity oxygen jet is directed onto the heated metal. This oxygen jet initiates an exothermic reaction with the iron in the steel, forming iron oxide, slag, while releasing additional heat, which sustains the cutting process. The oxygen stream also serves to blow away the molten slag, creating a clean cut. Cutting through 850 millimeters thick, mild steel requires significant preparation and specialized equipment, including a high-capacity torch and a steady, controlled oxygen supply to maintain the cutting efficiency. The process is slow due to the considerable thickness, with careful management of the cutting parameters, such as oxygen flow rate, torch speed and nozzle size to ensure a smooth and precise cut. Moreover, maintaining the appropriate cutting speed is crucial to avoid slag accumulation and ensure the cut's quality. This method is highly effective for heavy-duty industrial applications where thick steel plates need to be cut efficiently and with precision. Cutting 47 kilograms rail using oxypropane cutting equipment is a common method due to its efficiency and effectiveness. The process involves a combination of oxygen, oxy, and propane gases, which are mixed and ignited to produce a high-temperature flame capable of cutting through metal. In this scenario, the oxygen is supplied at a pressure of 350 kilopascals, while the propane is at 100 kilopascals. These specific pressure settings are crucial to achieving the optimal flame temperature and ensuring a clean, smooth cut. The high-pressure oxygen, when mixed with the lower-pressure propane, creates a flame that reaches temperatures sufficient to melt the steel rail. The cutting process begins by heating the rail's surface to its ignition temperature using the oxypropane flame. Once the rail is sufficiently heated, a high-pressure stream of oxygen is directed at the heated area, causing rapid oxidation. This oxidation process produces molten iron and slag, which is then blown away by the force of the oxygen jet, creating a clean cut. A 47-kilogram rail, due to its thickness and density, requires precise control of the cutting parameters. The proper alignment of the cutting torch and maintaining consistent pressure is essential for an even cut. The use of oxypropane is favored over other methods due to its cost-effectiveness and the relatively lower flame temperature, which reduces the risk of warping or distorting the rail. Oxypropane cutting is a reliable method for cutting heavy-duty materials like rail, offering a balance of precision, speed, and economy. When you think of chains, your mind might immediately jump to jewelry, like a necklace. However, there are chains designed for far more demanding tasks, such as those used in mining. These industrial chains are massive, with some links weighing up to 20 kilograms. The manufacturing process of these chains is complex, requiring precision and strength at every step. The process begins with raw steel rods, each 8 meters long. These rods are cut into 33 centimeters sections, which will eventually form the individual links of the chain. The steel used is of a special grade, selected for its ability to endure the harsh conditions found in underground mining. Once cut, the steel sections are heated to around 600 degrees Celsius in an induction furnace. This rapid heating prepares the metal for shaping, making it malleable enough to bend but still strong enough to retain its integrity. The glowing sections are then bent into rough ring shapes, which are the precursors to the final chain links. Next comes the crucial welding process. A machine welds each link, and sparks fly to remove any impurities from the welding surfaces. This ensures that the welds are strong and free from defects, which is vital for the chain's durability. The workers responsible for this stage have a tough job, handling up to 650 chain links each day. After welding, the links are sent to a forge where they are pressed under 200 tons of pressure to form what are known as flat links, a common type used in mining chains. During assembly, the rod is bent to leave a small opening. This opening allows for the insertion of the next link, whether a flat link or a round link, which is then welded and pressed together. The chain grows piece by piece, with 2 workers handling 4 strands simultaneously. By the end of a shift, they produce roughly 100 meters of mining chains. TLA, a company based in Iserlohn, Germany, is one of the world leaders in manufacturing mining chains. These chains are used globally in underground mining operations. However, to bring coal to the surface, additional components known as scrapers are attached to the chains. These scrapers, also forged in Iserlohn, Kaiserlohn are made by shaping the glowing metal with a massive forging hammer, followed by a press that punches out the scraper blank. The blanks must cool overnight before they can be further processed. Meanwhile, the larger chains undergo a hardening process. They are heated to 900 degrees Celsius and then quenched in water, which significantly increases their strength. The smaller chains are processed differently. Steel wire is fed into a machine that quickly forms the wire into connected links. This process is fully automated, with the machine welding the links together, leaving only the task of placing them aside to a worker. Once the chains are assembled, they are subjected to rigorous testing. Each link is measured and, if necessary, adjusted to within 1/10 of a millimeter. The chain is then subjected to a tensile test, where it is stretched by several hundred tons of force. The goal is to ensure that the chain can withstand extreme stress. In one such test, a chain was stretched by about 1 centimeter under nearly 100 tons of force, but it only broke when the force reached 253 tons, proving its durability. Finally, to protect the chains from rust, they are dipped in a tectile bath. This substance forms a flexible and dense wax film around each link, providing long-lasting protection. With this final step completed, the chains are ready for shipment, with destinations as far away as Australia. The entire process, from cutting the raw steel to the final protective coating, ensures that these industrial chains can handle the demanding environments of mining operations worldwide. Lifting, lowering, and transporting chains have been vital since ancient times, with significant advancements occurring during the industrial era. Initially used in mining and agriculture, chains became widely available due to industrial manufacturing, expanding their use across various sectors. The Rudd Group, a global leader based in Swabia, Germany, has been at the forefront of chain system innovations for over 140 years. Their main production facility in Aalen manufactures high-quality chains ranging from 3 to 40 millimeters in diameter, processing over 1 million welded parts daily. In the 21st century, round steel chains have evolved into high-tech products for diverse applications. RUD's lifting equipment ensures the safe handling of heavy loads and meets the highest standards when paired with appropriate lifting gear. The company rigorously tests each chain during production, including weld seam inspections and system component drop forging, to ensure top-notch quality. RUD's core competencies include forming, welding, heat treatment, surface technology, forging, and machining, all aimed at delivering innovative, customer-oriented solutions with the highest safety standards. Heat treatment is a critical process in chain production, ensuring durability under extreme conditions. Every safety-relevant component undergoes thorough crack testing before final processing and global distribution. Rudd employs over 500 people at its Aalen site and around 1,700 specialists worldwide, relying on their expertise to maintain product excellence. A notable advancement by Rudd is the development of the patented ice material, which offers a 60% higher braking strength than grade 8, while maintaining the same elongation and fatigue resistance. The casting process in steel manufacturing begins with molten metal being transferred from a furnace to a ladle, which is then moved to the casting area. In this phase, the molten metal is poured into a mold, where it begins to solidify into the desired shape. This method ensures that the metal is formed with minimal impurities, achieving the necessary consistency and quality for further processing. The continuous casting process is a more advanced and efficient technique used to produce long strands of metal, typically in the form of billets, slabs, or blooms. After the molten metal is transferred to the ladle, it is carefully poured into a tundish, a container that regulates the flow of metal into the mold below. The tundish plays a crucial role in maintaining a steady supply of molten metal to the mold, while also acting as a reservoir to catch any impurities or slag that might rise to the surface. Once the molten metal enters the mold, it begins to cool and solidify on the outer surface while still remaining molten internally. The partially solidified metal, now known as the strand, is continuously withdrawn from the bottom of the mold at a controlled speed. It passes through a secondary cooling zone where it is further solidified using water sprays or mist cooling systems. The strand is then guided through a series of rollers to maintain its shape and prevent deformation. Billets are semi-finished steel products, typically rectangular or square in cross-section, used as raw material for rolling into bars, rods, and other steel products, offering uniform composition and quality. Completely automatic raw material handling systems streamline the movement and processing of materials like iron ore, scrap metal, and billets within the plant. These systems use conveyors, cranes, and robotic arms controlled by advanced PLC systems to ensure efficient, precise, and safe handling, reducing human intervention, minimizing errors, and optimizing production flow. A reheating furnace is a critical component in steel production used to heat semi-finished products like billets, slabs, or blooms to a uniform temperature before they undergo rolling or forging. Operating at temperatures around 1100 to 1300 degrees Celsius, the furnace ensures the steel is malleable enough for shaping. It uses fuels like natural gas or oil and is designed for efficient heat transfer, minimizing fuel consumption and optimizing the steel's mechanical properties during subsequent processing. The rolling process involves compressing heated steel between rotating rolls to reduce its thickness and shape it into desired forms. Main roughing is the initial stage in the rolling process where large, heated billets are passed through roughing mills to reduce their size and prepare them for further shaping. This stage is crucial as it sets the foundation for the final product's dimensions and quality. During main roughing, the steel is passed through a series of large, heavy-duty rollers that apply substantial pressure to gradually reduce the billet's cross-sectional area. The process is carefully controlled to ensure consistent reduction across the length of the billet, which helps in maintaining uniformity and avoiding defects like uneven thickness or surface imperfections. The roughing mills are typically equipped with hydraulically pre-stressed stands to handle the significant forces involved. The output from the roughing stage is a rough-formed bar or slab that is still relatively thick and requires further processing in intermediate and finishing mills to achieve the final desired dimensions and mechanical properties. Hydraulically pre-stressed stands are robust rolling mill structures where hydraulic pressure is used to preload the rolling components. This ensures stability, reduces vibrations, and enhances precision during the rolling process. A PLC-controlled cobble shear is an automated cutting system used in rolling mills to remove deformed or defective sections of steel bars or billets, known as cobbles. Controlled by a programmable logic controller, PLC, it ensures precise real-time cutting, preventing damage to the equipment and maintaining production efficiency and safety. A housing-less vertical stand is a compact, open-frame rolling mill stand that allows for easier roll changes and maintenance. It provides high rigidity and precision, essential for consistent product quality. Slit rolling technology from Morgard's Hamar uses advanced high-speed techniques to efficiently produce narrow, high-quality steel sections with reduced material waste. A straight-line mill continuously rolls steel bars in a linear path, ensuring uniform shape and dimensions through precision-guided rollers. PLC-controlled loopers are automated systems in rolling mills that manage and adjust the tension of the steel as it moves through the mill, ensuring smooth, continuous rolling and preventing defects. The high-yield quenching and self-tempering treatment box rapidly cools steel bars with controlled water spray or mist to enhance strength. It also facilitates self-tempering, allowing bars to achieve optimal mechanical properties and uniform hardness, improving their performance and durability in structural applications. The PLC-controlled dividing shear precisely cuts steel bars to exact lengths using automated control systems. This ensures accurate length control, reduces waste, and enhances overall production efficiency. The main control desk is the central hub for monitoring and managing plant operations. It integrates various systems and controls, providing operators with real-time data and automated control over production processes. The automatic rake-type cooling bed uses automated rakes to evenly distribute and cool hot steel bars. It ensures uniform temperature reduction, prevents warping, and facilitates efficient handling and sorting. The PLC-controlled cold shear is an automated cutting tool used in rolling mills to cut steel bars into precise lengths. It operates using a programmable logic controller, PLC, to ensure accurate, consistent cuts while minimizing waste and improving efficiency. The system enhances safety and reduces manual intervention by automating the cutting process. The automatic chain transfer system from Sunbursta, Sweden, efficiently moves and transfers steel products through various stages of production using automated chains, ensuring smooth, reliable material handling with minimal manual intervention. Automatic bar bending and bundling systems streamline the process of shaping and packaging steel bars. These systems use advanced robotics and programmable controls to bend steel bars into specified shapes with high precision and consistency. Once bent, the bars are automatically sorted and bundled according to size and specifications. The bundling process is also automated, ensuring that bars are securely tied into neat bundles for easy handling and transportation. This automation reduces manual labor, enhances safety, and increases production efficiency by minimizing errors and optimizing the organization of finished products. The 6 electrical overhead traveling cranes are essential for lifting and moving heavy steel components within the plant. They operate on overhead tracks, providing precise, efficient handling of materials across different production areas, enhancing workflow and reducing manual handling. The Tenaris Bay City seamless pipe manufacturing process is a modern marvel of industrial efficiency and technological advancement. In the hot rolling mill process, billets are heated to 1,250 degrees Celsius to 1,280 degrees Celsius in a rotary hearth furnace. The Mannesmann effect, named after the Mannesmann brothers, involves using a barrel-type piercer to transform the heated solid steel billets into hollow blooms. This process applies radial and axial forces to create a hollow cavity, effectively reducing the billet's diameter while elongating it. The result is a hollow bloom that can be further processed into seamless pipes with precise dimensions. In the heat treatment phase, the austenitizing furnace plays a critical role. Pipes are reheated in this furnace to temperatures above the austenite transformation point, typically between 850 degrees Celsius and 1000 degrees Celsius. This high temperature allows the steel to transform into austenite, a phase that enhances its ability to absorb carbon and improves its overall ductility. By achieving this uniform temperature, the steel structure becomes more amenable to subsequent quenching and tempering processes. The austenitizing furnace ensures that the entire pipe reaches a consistent temperature, which is crucial for maintaining uniform mechanical properties and strength across the entire length of the pipe. This step sets the foundation for achieving the desired hardness and toughness in the final product. The finishing stage of the seamless pipe manufacturing process ensures that each pipe meets rigorous quality standards and customer specifications. Each pipe is subjected to hydrostatic testing, where it is filled with water and pressurized to check for leaks and verify its strength under specified pressure conditions. This test ensures that the pipe can withstand the pressures it will encounter in service. Using electromagnetic waves, this method detects any internal or external defects in the pipe. The process involves passing the pipe through a coil that generates electromagnetic fields to identify inconsistencies. High-frequency sound waves are employed to measure wall thickness and detect any internal flaws. This non-destructive test provides detailed information about the pipe's integrity and consistency. Pipes are faced, beveled, and threaded using automated equipment. This step prepares the pipe for connection with other pipes or components, ensuring precise dimensions and alignment. Specialized automated equipment assembles the pipe with couplings, ensuring a secure joint. This test checks for any obstructions within the pipe that might impede the flow of materials. To protect against corrosion during storage and transport, pipes are coated with lacquer or varnish. Aurora Iron and Steel Rolling Mills operates a 300,000 TPA combination mill specializing in special bar quality, SBQ steel. Handles billets in sizes of 160 by 160 millimeters, 200 by 200 millimeters, 250 by 250 millimeters, 300 by 300 millimeters, and 320 by 250 millimeters. These billets are processed to produce wire rods ranging from 5.5 millimeters to 16 millimeters, and straight bars ranging from 12 millimeters to 140 millimeters. In the roughing 1 stage, an automated manipulator or trough is utilized for bar feeding. This system efficiently positions and guides the heated billets into the rolling mill, ensuring precise alignment and smooth transition through the rolling stands. The automation enhances process accuracy and reduces manual handling, improving overall productivity and consistency. In the roughing 2 stage, the rolling process involves turning the bar at a 45-degree angle to feed it diagonally into the mill. This precise angling allows the mill to effectively shape the bar into equal-sized squares, which is crucial for maintaining uniformity in the final product. The diagonal feeding technique enhances the rolling efficiency by evenly distributing the pressure across the bar, resulting in consistent dimensions and improved mechanical properties in the finished steel products. This step is essential for producing high-quality special bar quality, SBQ steel. The intermediate mill stage features 6 housingless stands arranged in an HV horizontal-vertical configuration. This setup allows for flexible and precise rolling, where the horizontal and vertical rolls work together to progressively reduce the bar size while maintaining its shape. The housingless design enhances mill stability, reduces vibration, and improves product accuracy, making it ideal for producing high-quality special bar quality SBQ steel. The crop and cobble shear is a crucial component in the rolling process, used for trimming the ends of the rolled bars and removing any defects or irregularities. This ensures that the final product is of uniform length and free from imperfections, enhancing overall product quality and consistency. The finishing mill features 6 housingless stands arranged in an HV horizontal-vertical configuration, designed for precise and consistent final shaping of the bars. Vertical loopers are integrated into the process to manage the bar tension, ensuring smooth material flow and optimal control, resulting in high-quality, accurately dimensioned finished products. Crank cum flying shear. Turnover-type cooling bed with automated bar shifter. Run-in roller table with braking slide automatic rake type cooling bed. The manufacturing of rollers and pulleys involves a meticulously orchestrated process designed to produce high-performance components for both heavy-duty and high-precision applications. At the heart of this operation is a sprawling site with a surface area of 16,000 square meters. Automatic storage systems use robotic technology and automated conveyors to efficiently store, retrieve, and manage inventory with precision and speed. Careful checking of incoming products involves thorough inspections for defects, dimensions. Rollers and pulleys both for heavy-duty and high-precision applications. Automatic manufacturing with high levels of accuracy utilizes advanced CNC machines and robotics to precisely control every step of production, ensuring consistent quality and exact specifications for each roller and pulley. High-performance products are engineered for durability, precision, and reliability, meeting stringent standards for demanding applications like distribution centers and airports. Efficient robots handle repetitive tasks with speed and precision, while specialist personnel ensure optimal operation and quality control throughout the manufacturing process. Dynamic warehouses are designed for flexibility and efficiency, incorporating automated systems for real-time inventory management and rapid retrieval. They use advanced technologies such as conveyor systems, automated guided vehicles, and robotics to adapt to changing demands, optimize storage space, and streamline the flow of materials throughout the facility. CNC lathes precisely shape rollers and pulleys by controlling rotational cutting tools, while balancing machines ensure components are perfectly balanced to reduce vibrations and enhance performance in various applications. Pulleys, rollers, and motor rollers facilitate smooth, efficient material handling in distribution centers and airports, ensuring reliable operations and minimal downtime.